From the universe's fiery beginnings, when it buzzed with limitless energy, to the first minutes that still burned at over 180 million degrees Fahrenheit, the cosmos was a cauldron of plasma, a superheated mixture of particles and radiation. However, everything changed when the universe, some 400,000 years old, cooled to approximately 5,400 degrees Fahrenheit, or 3,000 Kelvin. It was at this point that a small amount of energy was released in the formation of a hydrogen atom, giving rise to a particle we know as a photon, a messenger of light. As the universe transformed from plasma to neutral gas, light began to flow freely, marking the beginning of an epic journey for these photons. They went through the so-called Dark Ages, a period before the birth of the first stars and galaxies. Around them, the first stars were awakening, massive and ephemeral, and the first supergiant black holes were emerging, devouring everything around them. Galaxies began to form, illuminating the sky with the lights of countless young stars, which fused hydrogen and helium into heavier elements. Just imagine, each photon, born and dying, colliding with speeding particles before it could even travel. But after the calm of the Big Bang, one photon in particular began its epic journey through time and space. It passed through generations of stars until it reached our sun and, billions of years later, found Earth, our little rocky home. Isaac Newton carefully observed how light traveled through lenses and reflected off mirrored surfaces, fascinated by the phenomenon of refraction, where light changes direction as it passes from one medium to another. For him, light behaved like a wave, oscillating through the universe. Let's simplify this. Imagine a child on a swing. It moves back and forth like a pendulum, and each swing is an oscillation that we can predict. Now think of a stone thrown into a quiet pond. It creates ripples that move outwards, each circle pulling the next. This is how earthquakes shake our Earth's crust, and similar waves disturb the solar atmosphere. And so, light also seemed to be a wave. But this raised an intriguing question. If light is a wave, what exactly is it rippling? In 1800, the English physicist Thomas Young directed light through two narrow slits and observed an intriguing interference pattern. How could Newton's vision of light as particles explain such interference? It was as if tiny bullets were passing simultaneously through two openings, something unthinkable. Meanwhile, other research was being done into the wave nature of light, including polarization through the mineral calcite. Calcite has special optical properties, such as birefringence, which allows it to split an incident ray of light into two polarized rays that follow different paths. This phenomenon is useful for exploring and demonstrating the wave nature of light, which helped to challenge and expand the scientific understanding of the time, which was predominantly influenced by Newton's theories about light being composed of particles. The contribution of James Clerk Maxwell, a 19th century Scottish physicist and mathematician, was in the study of electric and magnetic fields. He didn't see electricity and magnetism as separate forces, but as parts of a whole. His great leap was to question the behavior of light in the vacuum of space. How does light travel through nothing? Maxwell's equations showed that when an electric or magnetic field is disturbed, these disturbances don't simply disappear. They generate each other, oscillating and propagating like waves in a calm lake. But what actually caused these waves to propagate? Maxwell concluded that it was the electric charges, the electrons, that did all this. As they vibrate, they create disturbances in the fields around them, and these disturbances, these waves, are what we perceive as light. When Maxwell realized that the light we see is only a fraction of what exists, he predicted that there would be forms of light with longer or shorter wavelengths than our eyes can detect. Thanks to this, today we know that the electromagnetic spectrum is vast and wonderful, ranging from radio waves to X-rays. In 1886, in the heart of the University of Karlsruhe, German physicist Heinrich Hertz, in a laboratory buzzing with ideas and experiments, discovered something revolutionary. Hertzian waves, or as we know them today, radio waves. Hertz used an oscillator to create electromagnetic waves and a resonator to detect them, showing that these waves propagated in space and had properties such as reflection and refraction, similar to those of visible light. In addition, Hertz's experiments paved the way for the development of radio and wireless communication technologies. The units of radio frequencies, called hertz, were named after him as a tribute to his significant impact on science. In 1901, Wilhelm Conrad Röntgen was awarded the first Nobel Prize in physics. For what? For something that revolutionized not only science, but also medicine: X-rays. Imagine convincing someone to put their hand under an unknown beam to capture the first X-ray photograph. Röntgen did it with his own wife, Bertha. Through this incredible discovery, he showed the world that it was possible to see beyond the surface, to see what is hidden from our eyes. But despite these advances, there was still a long way to go to fully understand light. At the beginning of the 20th century, in a year that would go down in history as the Anno Mirabilis, 1905, Albert Einstein arrived on the scene and changed everything. While exploring the photoelectric effect, he discovered something that challenged the classical view. Light didn't just act as a wave, but also as particles, packets of energy that he called quanta. Quanta refers to the plural of quantum, which is a term used to describe the smallest discrete quantity of any physical quantity in quantum mechanics. In the context of light and the photoelectric effect, each quantum of light is called a photon, which is the smallest possible unit of light or any other form of electromagnetic radiation. Each photon carries a specific amount of energy, which is proportional to the frequency of the light. The color of the light determined the energy of these packets, explaining why red light, which is less energetic, couldn't eject electrons like blue light. Now, imagine light not just as something that illuminates, but as something that pushes. In 1923, Arthur Compton made an astonishing discovery that showed how light, X-rays to be precise, could literally push electrons by changing their energy and wavelength. This discovery proved that light was not only a wave, but also a particle. And speaking of pushing light, have you ever heard of Crookes's radiometer? This device, invented by English scientist Sir William Crookes in 1873, has small blades that rotate when exposed to light. Initially, it was thought that sunlight literally pushed the blades, but it was later discovered that the movement is more a dance between the heat and the gas inside the bulb. French physicist Louis-Victor Pierre Raymond, better known as Louis de Broglie, at one point faced one of science's greatest conundrums. Is light a particle or a wave? It was neither, it was both. When it travels, light behaves like a wave, forming interference and diffraction patterns. But when it interacts, it acts like a particle. And do you know the equation created by one of the greatest physicists of the 20th century, Paul-Adrien Maurice Dirac? This equation, known as the Dirac equation, suggested the existence of something totally new: antimatter. The idea is that for every normal particle, such as an electron, there is a corresponding particle, but with opposite properties. In the case of the electron, this would be the positron, which is almost identical to the electron, but with a positive electric charge instead of a negative one. Dirac explored ideas such as the magnetic monopole and also developed Fermi-Dirac statistics. Let's use an analogy to further simplify the concept of Fermi-Dirac statistics and the quantum behavior of electrons. Imagine you're in a movie theater where the seats are the energy levels in an atom and the people are electrons. According to the rules of this movie theater, which would be Fermi-Dirac statistics: 1. Each chair can only accommodate one person due to Pauli's exclusion principle, which states that two electrons in an atom cannot occupy the same quantum state simultaneously. So, if an electron is already occupying a chair, energy level, no other electron can occupy it. 2. People prefer to sit as far apart as possible until all the chairs in a row are occupied, before they start sitting together in pairs. This represents the distribution of electrons in the energy levels of an atom. They first fill the lower energy levels before moving on to the higher ones. Now, about the emission of photons when an electron changes energy level. Imagine that, when moving from a high chair, a higher energy level, to a chair closer to the screen, a lower energy level, the person drops a bright ball of light. This ball of light is the photon emitted. The distance the person moves between the chairs determines the color of the ball of light. Larger movements mean more energetic colors, such as blue, while smaller movements result in less energetic colors, such as red. Richard Feynman was an American theoretical physicist who not only helped develop the atomic bomb during the Second World War, but also reinvented the way we understand nature at the most fundamental level. In 1965, he was also awarded the Nobel Prize for Physics, making a significant contribution to quantum electrodynamics with his groundbreaking Feynman diagrams. Imagine a solitary electron surrounded by an invisible electric field. When this electron moves or vibrates, it interacts with this field. The great conundrum that Feynman faced was calculating how much energy was involved in these interactions. No matter how hard he tried, the answer was always infinity. In his Nobel Prize speech in 1965, he joked about how electrons don't act on themselves, but interact with each other through something very special, the photon. For example, if you think of an electron as a child on a slide, the straight line would be its normal path. But when that electron meets a photon, think of it as an imaginary friend. The line on the slide takes on a curve. This curve represents the change in direction of the electron due to the exchange of a photon. Now let's say you're on a super fast roller coaster, where everything around you is going by so fast that you can barely make out the scenery or the details. Now think of a photon, a particle of light, traveling through the universe at an incredible speed. The speed of light, which is about 186,000 miles per second, or approximately 300,000 kilometers per second. For this photon, the concept of time is completely different from ours. To explain it better, let's imagine that you can travel at the speed of light alongside a photon. While you're traveling, according to the theory of relativity, time for you practically stops. This means that, for the photon, the journey between stars and galaxies, which can take billions of years in our perception, happens instantaneously. It's as if it leaves one point and arrives at another without feeling the passage of time. Despite the vast distances it travels in the universe, it doesn't age for a single second. The speed of light is not only a speed limit for the universe, but also a barrier to our traditional understanding of time and space. Each photon that lights up our nights has traveled through the cosmos without aging a single day, while the universe around it has changed dramatically. Incredible, right? Don't forget to like and subscribe for more journeys through the fascinating world of science. See you in the next video. Bye.